Howdy! This is your friendly neighborhood physics teacher here, and we're going to go over your kinematic homework problems. So this is set B. Also in the end, I'm going to go over questions 16 and 17 on the mixed calculations. And I'll also do set B. So there is a chance that you're an 8A person who got B set, so this would be the video for you, or if you're a B-Day person and got A set on the mixed calculations, you want to go watch the other video. It's near the end. So let's go ahead and get started. So our first question is, a race car is traveling in a straight line, a race car is traveling a straight track at 150 meters per second. When the driver slams on the brakes and decelerates, hate that word, but decelerates accelerates in a negative fashion. So it's basically accelerating in the negative direction at a rate of negative 23 meters per second squared. So if we're doing our givens, A, so anytime you see acceleration or deceleration, that is your variable A, equals negative 23 meters per second squared. And also our initial velocity is 150 meters per second. Okay, looking at the meters per second, it doesn't say velocity anywhere. It just says it's traveling. The key thing I know it's velocity is because of the meters per second. Meters per second is velocity. Now, how did I know it was initial velocity? It's because it's at the beginning. It's starting there. That's the fastest it's going. So that is our initial velocity. Besides seeing the word acceleration or deaccelerates, I know that the negative 23 is acceleration because of the meters per second squared. Knowing your variables and units is very important. I'll give you the equation. You just have to know your variables and units. So let's then go to question 1, or this is question 1, question A of question 1. How long will it take to stop the car? Stop is another given. How fast are you moving if you're stopped? Exactly, 0. So, and that's at the end. So your final velocity is going to be 0. How long is asking for time. Think about if you ask how much longer do I have to be in this class, you're looking for the time. Now, equation. A lot of people are having trouble knowing what equation to use. So let's write out all our equations. We have our delta x equals VIT plus 1/2 AT squared. We have delta x equals 1/2 V final plus V initial times time. We have V final equals V initial plus 2, nope, not plus 2, plus A T. Then we have V final squared equals V initial squared plus 2A delta X. So those are our 4 equations. So the main thing, our equation has to have our time. It has to have time in the equation. If it doesn't have time in the equation, we cannot use it. So does the first one have time? Yep. Second one have time? Yep. Third one have time? Yep. Does the fourth one have time? Nope. So we can't use it. Now also, look at your givens and look at your equations. Make sure you have everything. So looking at the first equation, first variable is delta x. Do I see delta x anywhere? Nope, so can't use it. Looking at the second one, oh, there's that pesky delta x again. Can't use it. So we're left with the third equation, VF equals VI plus AT. Now we substitute. Final velocity is 0. Initial velocity is 150. Plus our acceleration, that negative matters, and you're looking for time. At this point, you are done with the physics. It's now purely algebra. It's now purely algebra. A lot of people try to add or subtract these two numbers together. You can't do that. You can't do that. The reason is because of this little guy right there. That t. The 23 is being multiplied by the t. The 150 doesn't have a t. So since the 150 doesn't have a t, it can't be added or subtracted. It has to go on the other side. It wants to get away. Run away. So what you do to one side, you got to do the other. And you're subtracting because it's a positive number. So we're left with 150. Negative 150 equals negative 23 times t. We still want t by itself. So since the negative 23 is being multiplied by t, what's the opposite of multiply? Yep, divide. And what you do to one side, you got to do the other. And then you pull out your handy-dandy calculator, and you do 150 divided by 23. Now, if you notice, I didn't mention the negatives because the negatives end up canceling out. You can go ahead and plug them in, but your negatives end up canceling out. And you're left with 6.52 seconds. This time is measured in seconds. If you put that into scientific notation, you do not have to move the decimal, so you're just left with 6.52 times 10 to the 0, because I didn't have to move the decimal, and that is your time. That is your standard and scientific notation answers. So now let's look at part B. Part B asks how far it will travel in this time. How far will it travel in this time? So our givens pretty much stay the same. Our initial velocity is 150. Our acceleration is negative 23. And this time we know time because we just solved for it. It's 6.52. Our final velocity is 0 because it's still trying to figure out how long it takes it to stop. And our unknown is delta x. We need that in meters. So let's look at our equations again. Which ones could we use? Now, we are looking for delta x. That's what we're looking for. So our equation has to have delta x in it. So if the equation does not have delta x, we cannot use it. Looking at it, number 3 does not have delta x. So we cannot use it. Well, we got to make sure we have all the givens. So we're looking for delta x. Check. We have VI, we have T, we have A. Looking at this, we can do any equation we want besides the third one. So let's use the second one. Seems like the easiest. Work smarter, not harder. So the equation is delta x equals 1/2 V final plus V initial T. We're looking for delta x. We're substituting. Our final is 0. Our initial is 150. Our time is 6.52. Again, at this point in time, we are done with physics. It's purely algebra. So do your PEMDAS. Parentheses come first. So inside the parentheses, you just get 150. And now you just multiply across. So you would do 1/2 times 150 times 6.52. And in your handy-dandy calculator, you get 489 meters. That is our answer in standard form. To put it in scientific notation, you have to move the decimal 2 times. So we're left with 4.89 times 10 to the 2 meters. So that is our standard and scientific notation. Part C asks for the velocity of the car after 2 seconds. So our givens, our initial velocity is still 150 meters per second. our acceleration is still negative 23 meters per second squared. At this point in time, all of our other unit variables are different. It gave us time, which is 2 seconds. And we're looking for how fast, or what is the velocity it's moving after it starts moving at 2 seconds. So we're looking for our final velocity. So our equation has to have final velocity in it. So let's look at our equations. If it does not have final velocity in it, we cannot use it. Guess what? The first one does not have final velocity in it. In our givens, we are not given delta x at all. So no delta x. So we cannot use anything that has delta x in it. That has a delta x. That one has a delta x. So the only one that's left is the third one. So our equation is going to be our v final equals v initial plus a t. We substitute. We're looking for v final. Our v initial is 150 plus our acceleration, which is 23, times our time, which is 2. Again, at this point in time, we are done with physics. It's purely algebra. So think about PEMDAS. So you have to multiply first. So you do 23 times 2, which gives you 46. Now that negative means instead of adding, you're going to end up subtracting. So you're going to subtract 46. And then you just do 150 minus 46, and you're left with 104. And that is in meters per second. So that is question C on number 1. That's in standard form. To put into scientific notation, we move the decimal over 2 times. And you're left with 1.04 times 10 to the 2, because we moved it over 2 times, meters per second. So that is our answer in standard and scientific. Question 2. Question 2 states, what is the acceleration of a bicycle that changes its velocity from 11.2 meters per second to 25.3 meters per second in 8.71 seconds? So givens. It says a change of velocity from 11.2. So we know it's velocity, but which one? Well, hopefully you said initial, because your initial velocity, because it comes first. Your final velocity would be 25.3 meters per second. And then it gives us in 8.71 seconds. So our time would be 8.71 seconds. At the very beginning, it says, what is the acceleration? So our unknown is acceleration. Let's go back to our handy-dandy, not handy-dandy calculators quite yet. Let's go back to our equations. So our equation has to have acceleration in it. It has to have acceleration in it. So if the equation does not have acceleration, we cannot use it. The second one does not have acceleration in it, so we cannot use it. Looking at our givens, we're not given delta x. We're not given delta x. So anything that has delta x in it, we cannot use. We cannot use that one. We cannot use that one. So it looks like we're using the third one again. So our equation would be v final equals v initial plus a t. Our v final is 25.3. We're just substituting at this point in time. Equals our initial, which is 11.2. Plus, we're looking for the acceleration. Your time is 8.71. We are done with physics. We're doing algebra at this point in time. Again, you cannot add or subtract these two together. The reason is because of our acceleration. Cannot because of the acceleration. Your 11.2 doesn't have an A, so therefore you can't add them together. So we have to bring the 11.2 on the other side, because what you do to one side, you got to do to the other. So we're left with A times 8.71. You get 14.1. We need the A by itself. The opposite of multiply is divide. What you do to one side, you got to do the other. Cancel out. So in your handy-dandy calculator, you're going to plug in 14.1 divided by 8.71. And you would get a 1.62 meters per second squared as your answer. To put that into scientific notation, you don't have to move the decimal at all because we already have 1 in front of the number. So it's just 0 meters per second squared is our acceleration. So that is your standard and scientific notation answer. And that's done for number 2. Number 3 is asking for displacement. And we have 2 different problems looking for displacement. So let's pull out our givens. For the first problem, it states it decelerates at a rate of negative 3.45 meters per second. So our acceleration, remember, because deceleration and acceleration both go to A, be a negative 3.45 meters per second squared. From a speed of 38.1 meters per second to a speed of 16.7 meters per second. So our initial velocity would be 38.1 meters per second, and our final velocity would be a 16.7 meters per second. The reason our initial velocity is the 38, the reason our final velocity is because that's the first one. The reason our final velocity is 16.7 because that is our second one. Another thing, look at your initial is bigger than your final, which makes sense if it's accelerating in a negative fashion. And we are looking for our unknown is a delta x. That is our unknown. So in our equation, we have to have delta x. We have to have delta x. So we're going to scroll up to our equations, and we need the equations that have delta x. If it does not have delta x, we cannot use it. So this equation does not have delta x. Also, looking at our givens, we are not given time. We are not given time. So any equation that has time in it, we can't use either. So the first one has time, the second one has time. So we'll be using the fourth equation. Our fourth equation is v final squared equals v initial squared plus 2a delta x. We substitute. Our final is 16.7 squared equals 38.1 squared plus 2 times negative 3.45 times delta x, which we're looking for. We're done with physics. Purely dealing with algebra now. So now you just do PEMDAS. So we have to square first. So we do 16.7 squared. And we're left with 278.89 equals, now we do 38.1 squared. And that gives us 14.1 or 1,451.61, and we could go ahead and multiply by 2 times 3.45, and that'll give us a negative 6.9 because of that negative delta x. And again, you cannot add those two numbers together because of the delta x. So you have to get the 5161 on the other side. And since it's adding, you subtract it. That cancels. So you're left with 278.89 subtract 1451.61, and that gets us a negative 1,172.72, and that equals a negative 69 times delta x. We want the delta x by itself. It's being multiplied. So the opposite of multiply is divide. And what you do to one side, you gotta do to the other. Then you just plug that into your handy dandy calculator. And you get 169.96 meters. To put it into scientific notation, you move the decimal over 2 times, and you get a 1.6. Oh, because of rounding, you actually get a 1.70 times 10 to the 2 meters because you moved it 2 times, and that equals our displacement. That is our standard in scientific notation. On the same problem, we have a second question. It says accelerates from rest at a rate of 7.63 meters per second squared for 21.1 seconds. So our givens is rest. Rest is a given. That is telling you your initial velocity is 0. Because think about when you're resting, are you moving? No. It gives you an acceleration of 7.63 meters per second squared, and it gives us a time of 21.1 seconds. And we're looking for our displacement. Again, looking at our equations, we have to have displacement in the equation. We have to have displacement in the equation. So if we're looking at our formulas, we have to have displacement in the equation. The only one that doesn't have displacement is that one. But we also do not have final velocity. It's not given. So we cannot use these two because they both have final velocity. We have to use the first one. So our equation is delta x equals vi times t plus 1/2 at squared. We're looking for delta x. We're just substituting. Our initial velocity is 0. Our time is 21.1 plus 1/2. Our acceleration is 7.63. Our time is 21.1. Don't forget the squared. We're completely done with physics at this point in time. It's now algebra. 0 times anything is 0. We have to do the squared first. So you end up getting 21.1 squared. And that equals a 445.21. And now you can just multiply across the board. And you multiply it by 1/2 times 7.63 times 445.21, and that gives you 1,698.48 meters. If you look at your key on the homework, that key is wrong. This is the correct answer. We did take that into consideration while grading. So putting that into scientific notation, you have to move the decimal over 1, 2, 3 times. And you get a 1.70 times 10 to the third meters. And that is question 3. So our last problem is exactly like the first one. A spaceship is traveling above the Earth at 520 meters per second when it must decelerate to enter the Earth's atmosphere. So a given, we have initial velocity, which is 520 meters per second. And then part A, it states, if its acceleration is negative 53 meters per second squared, so that is our acceleration, how long will it take to stop? Remember, stop is a given. Stop is a given. It means your final velocity is 0. Stop before it hits the Earth's atmosphere. So how long? How long? We're looking for time. We're looking for time. So since this is exactly like the first one, we're going to use our VF equals VI plus AT. Our V final is 0. Our V initial is 520 plus our acceleration, which is negative 53, times time. We cannot add or subtract those two numbers together, the 520 and the negative 53, because of the t. So we got to figure out how to get 520 on the other side. It's a positive number, so we're going to subtract. And what you do to one side, you got to do to the other. And then we need t by itself. It's being multiplied, so the opposite of multiply is divide. And you're left with t equals 520 divided by 53. You plug that into your handy dandy calculator and you're left with 9.81 seconds. Putting that into your scientific notation, you get 9.81 times 10 to the 0 because you didn't have to move the decimal. There was already one number in front of it. So that's part B. Part A. Part B states how far will it travel in this time. So our givens stay the same. Our initial velocity is still 520 meters per second. Our final velocity is still 0 meters per second. Our acceleration is still negative 53 meters per second squared. And we just figured out our time. Our time is 9.81 seconds. And we are looking for how far. We're looking for our delta x. Looking at our equations, we have everything. So we can use any equation except for 3. Why can't we use the third equation? Yep, you got it, because does not have delta x. So let's use the first one. So delta x equals VIT plus 1/2 AT squared. Now we're just substituting. Our initial velocity is 520. Our time is 9.81. Our acceleration is negative 53. Our time is 9.81 squared. So now you just work through it. So you do 520 times 9.8, and you get 5,096. That's going to be subtracted by, you do 9.81 squared times 53 times 1/2. and you're left with 2,550.25, 26, and then you just subtract those two numbers. So 5,096 minus 2,550.26, and you're left with 2,545.74 meters. To put that into scientific notation, you have to move the decimal 1, 2, 3 times, and your answer is 2.55 times 10 to the third meters, because we move the decimal 3 times. That is your answer in standard and scientific form. Last question. The velocity of the space shuttle after 3 seconds. So our givens, initial stays the same, because that's what it starts at. Our acceleration stays the same, because that's what it's accelerating at. But this time, it gave us a different time. It wants to know how fast it's moving after 3 seconds. And so how fast it's after, so it's our final velocity. And we'll be using the third equation once again. So VF equals VI plus AT. We're looking for VF. Our initial is 520 plus our acceleration, which is negative 53, times time. Can't add or subtract, so we have to turn. Oh, nope. My brain went on autopilot there. We know time. We know time. I'm trying to say we don't know time. Our time is 3 seconds. So now you just plug it in. Let the calculator do the hard work for you. So you do 53 times 3, and you're left with 159. Then you do 520 minus 159, and that gives you 361. That is your final velocity. To put that into scientific notation, you move the decimal over 1, 2 times. So you're left with VF equals 3.61 times 10 to the 2, because we moved it 2 times, meters per second. So that is our answer in scientific and standard form. So that is it with the homework. But I did promise I will do questions 16 and 17 on the mixed calculations. So I'm on mixed calculations set B and on 16. So I'm doing question 16. So Sarah throws a ball straight up in the air with an initial velocity of 25.86 meters per second. How long will the ball be in the air before Sarah catches the ball? Assume she catches the ball at the same position that she threw it from. So let's kind of draw it out. So she threw the ball, it went up, came back down, she caught it at the same exact height. If you think about how the ball is acting at the very tippy top, it's stopping, because it has to stop before it starts coming right back down. So our initial velocity, I wrote final, so our initial velocity would be 25.86, and our final velocity will be VF, because we're just trying to find the time it takes it to go up right now. So a given would be initial velocity, final velocity, and since it's in the y direction, what's affecting it? Acceleration due to gravity. So that'd be a negative 9.8 meters per second squared. And we are looking for time. So looking at our equations, yep, we're using that pesky third one again. So final velocity is 0. Initial velocity is 25.86 plus acceleration, which is negative 9.8, and we're looking for time. Can't add or subtract those two numbers. We have to bring the 25 over here. So we're left with negative 25.86 equals negative 9.81 divided by t. So we have to move the negative 9.8 onto the other side. And you plug that into your handy dandy calculator. And you get a 2.64 seconds. But that is just for it going up. As for the total time it was in the air before she caught it. So we have to take consideration of it going down. So in theory, this time just becomes half time. So our total time would be that doubled, which will give us a 5.27 seconds. So that's 16. 17. So question 17 kind of comes off of this problem. So Sarah throws the ball up, but in this case she misses, and she lets the ball hit the ground an extra 1 meter. 1 meter. And we want to know how long it was in the air for. For us to do that, we need to know how far it fell from top to bottom. We need to know how far it fell from top to bottom. And we know the bottom half, but we need to figure out the top half. So we need to figure out the delta x of the top half, and then we can add the 1 to it, and we can get the total displacement. So our givens. Our initial velocity is going to be 0 this time, because we're going from top to bottom. Our final velocity, our initial velocity is 0 when it's at the very top. So our initial velocity is going to be 0. Acceleration is still negative 9.8 meters per second squared, because that's the acceleration due to gravity. We're on Earth, so gravity stays constant, which is 9.8. We have the time it took to fall. Well, only half of it. Our time was 2.64 seconds. And we need our delta x. Looking at our equations, we're going to end up using our first equation. Delta x equals VIT plus 1/2 AT squared. I came up with that because we do not have final velocity. That is the only equation that does not have final velocity. If we substitute, we have delta x equals 0 times 2.64 plus 1/2 negative 9.8 times 2.64 squared. 0 times anything goes to 0. That goes away. And so we're left with this part. Half of 9.8 is 4.9. 2.64 squared equals 6.97. You multiply that, and it gives you 34.15. Negative. That negative makes sense because it's going down. Remember, negative is just direction. From there, we can add our 1 meter. So we're left with a 35.15 meters. So that is our total displacement. So 35 is our total displacement. From there, we can find the time of the whole entire displacement. Our givens, our initial velocity is still 0, because it's still 0 at the top. Our displacement is negative 35.15 meters. Remember, it's negative because it's going down. Our acceleration is negative 9.8 meters per second squared. And we are looking for time. That's our unknown. Again, we are going to use our first equation. So delta x equals VIT plus 1/2 AT squared. Our displacement is 35.15. Our initial is 0. We're looking for time plus 1/2. Our acceleration is negative 9.8. And our again, we're looking for time squared. 0 times anything goes to 0. Half of 9.8 is 4.9 t squared. We need to get the t squared by itself. So we divide. What you do to one side, got to do to the other. So you're left with t squared equals, and you just do 35.15 divided by 4.9. The negatives end up canceling, so that gives you 7.17. We have to get rid of that squared. So do not forget to square root. Do not forget to square root. And that gives you 2.68 seconds. Now that is the whole entire time it took to fall going down. But remember, it's asking for the whole entire time the ball was in the air. So we have to take consideration of it going up. So that's where our half time comes into consideration. So it'd be 2.64. So to get our total time, we just add it by 2.64. And you get your total time, 5.32 seconds. There we go. Hope that helped. If you have any other questions, please ask Miss Heath or Miss Verona. Have a wonderful day. Bye.